This lesson is on solution stoichiometry. Yes, we can utilize stuff that we know about solutions now to execute stoichiometry problems. You're like, stoichiometry is all over chemistry. It really, really, really is. But before we get started, tough stoic, here's a joke. It says, what do you call a tooth in a glass of water? A 1 molar solution, which is hilarious, but also a wonderful preview in terms of how does maybe molarity come into play with maybe as an aid on solving stoichiometry problems involving solutions. So since I like to do stoichiometry with my green representing my given amount and my red representing my ending amount, if you want to use colors, I have my colors. We need our calculator, we need our periodic table, we need all that stuff. So let's get going and do a couple of practice problems here at the end once we establish what it is that we're doing here. Regardless, I don't care what type of stoichiometry you're doing, gas, solutions, acids, and bases, all stoichiometry problems start with a balanced equation. We need those coefficients from the balanced chemical equation to be used with a mole ratio. We've learned recently this concept of molarity, which is a way to express how concentrated a solution is, meaning how many moles of solute particles you have in a certain volume or liter of solution. Some more jokes. I'm in your volumes, affecting your concentrations. That cute little mole. And then here we have a 2 moles per liter solution. All right. So how are we using molarity here with solution stoichiometry? Okay, well, this is not new. Mole ratio. We know that is why those coefficients are super important, right? We need them to execute going from my giving substance to my ending substance, okay? This top arm, we've used this since the beginning. We know we can go from grams to moles using the molar mass, or I can convert from my in moles to grams using the molar mass again. The new part we are adding in today is here I'm going to be able to go from liters of an aqueous solution to moles, okay, using the molarity. I can also take it from my in moles to the liters of that aqueous solution, or that volume of that aqueous solution, using molarity. Once again, you were like, what does that even mean? Okay, well, here's some steps. When we get down to the practice problems, these steps will make a lot more sense. I'm just going to read them right now. So in these problems, if I've given you a volume and a molarity of your given substance, you can convert from that volume to moles of that substance using molarity as a conversion factor. What that means, well, first of all, if I say I have a 2 molar solution, we know that means that there are 2 moles in every 1 liter. That is a split unit that I can utilize as a conversion factor. Orienting it that way would allow for me to convert from moles to liters. We'll see that example here in a second. Well, then that would put me at moles of my given, and then I can stoic it out no matter where I need to go, just like normal. A second scenario, if I'm asked to find a volume of an unknown solution, and I've told you what its molarity technically is, I can use stoichiometry just like normal from my given guy to get to moles of that ending guy, and then I can use its molarity as a conversion factor oriented the opposite way to convert to that volume in liters. You're like, molarity is a conversion factor. Can you show me a little bit more about what that looks like? Yes, I can. So let's just say in general, if I wanted how many moles are in a 4 liter 2 molar NaOH solution, that molarity is a conversion factor. I can take that 4 liters and use that 2 moles per every 1 liter of NaOH split like a conversion factor. That's what 2 molar means, 2 moles in every 1 liters. Then my liters cancel off. The remaining unit on the top is moles. That allows me to convert from liters to moles. And similarly, it can allow for you to convert from moles to liters as well. Meaning if I've given you 8 moles of a 2 molar solution and I say how many liters would that occupy, you do the same thing. I use the same conversion factor, except I just have to flip it in the opposite direction to where the moles part cancels off, and I'm now able to solve for liters. So we're going to be utilizing this, but within a longer chain of conversions of stoichiometry now as well. So let's bounce on down to the document camera. and see if we can, do some of these problems. I think we can. We seem smart today. So I've got some problems, and these problems, I'm going to let you know that they seem a little bit more like, oh my gosh, there's lots of numbers here. Now on my map, my choices of units I can start with or end with are grams or liters. Grams are liters. So anytime you see a molar or a molarity value, I'm going to hang on to that and use that potentially as a tool or a conversion factor if I need to help me convert from moles to liters or liters to moles. So let's see what we got. Okay, how many grams of silver chloride will precipitate? So there's no chemical reaction for me. I need to first write my chemical reaction equation. So who are the players here? Who is starting who? I say how many grams of silver chloride will precipitate if 50 milliliters of silver nitrate is my first reactant and reacting with excess magnesium chloride. So I've mapped out who my reactants are. It is silver nitrate and magnesium chloride. Silver nitrate, if you'll remember, is an ionic compound between silver, who has a +1 charge, and nitrate, the polyatomic ion, with a -1 charge. So my formula for silver nitrate is a 1-to-1 ratio of those ions, AgNO3, okay? If you want, you can specify that it is aqueous, because I told you it is a solution. As a review, when we write aqueous of an ionic compound, it is understood that those silvers and those nitrates are existing as their ion forms in solution. Okay, that's my first guy. My second guy is magnesium chloride. That's not too tricky. Magnesium, he's just a group 2 metal with a +2 charge. Chlorine is just plain old chlorine, a group 17 nonmetal with a -1 charge. So that means the ratio of magnesiums to chlorines I need in that ionic formula is MgCl2. I need 2 -1 charged chlorines to cancel off 1 positively 2 charged magnesium. And it's a solution. Okay, so we got 2 aqueous solutions. Y'all, this looks like it's going to be a double replacement reaction for me. And in fact, judging by what they told me here in the problem, they're saying one of the products, silver chloride, will precipitate out. Yes, it's a precipitation reaction. But let's go ahead and check. We know that in this double replacement reaction, that is a precipitation reaction, that silver is going to pair up with now the other anion, the chlorine, getting rid of the subscripts. They do not matter. I'm going to form a brand new chemical formula between silver and chlorine from scratch according to what their charges are. We mentioned that silver has a +1 charge and chlorine as an ion has a -1 charge. So my first product is going to be AgCl2. I can check my solubility rules and notice that silver chloride, a halide, is actually going to be an exception to being soluble, which is where we identified this as being the precipitate that they mentioned in the problem. Okay, then my second product is going to be the couple formed between the nitrate and the magnesium. The metal cation goes first, the nonmetal anion goes next, so magnesium's up first, nitrate's up next. What's the charge of magnesium? +2. What's the charge of nitrate? -1. So I have a how many magnesiums do I need? I need 1 magnesium, but how many nitrates do I need to neutralize that charge? I need 2 of those. So I take the +2 charge of the magnesium and the -1 charge of the nitrate, so that means I have a 2 of the nitrates on the bottom. All nitrates, according to my solubility rules, are soluble, so we get to go AQ. Okay, if we wanted to, we could expand this out into a net ionic equation showing the dissociation of ions, but we will not do that today because we're doing some stoichiometry with this. But I almost forgot to balance, you guys. Oh my gosh. And I intentionally put blanks there so I won't forget, but I almost did forget. Okay, so we have, who do we know? 2 chlorines on the reactant side, only 1 here. Uh-oh. So I put a 2 in front of silver chloride, which means now I have 2 silvers. Uh-oh, I need 2 silvers then over here. So I put 2 in front of silver nitrate, which means now I have 2 nitrates. We already have 2 nitrates. Everybody looks balanced. Okay. Had to do that first, and now I'm ready to read the ding-dang problem and be like, what stoichiometry are we doing today? Okay, I always, with my red, I block off or box off what it is they're asking me to solve for, because this will represent something on this ending side of my stoichiometry map. So when they say how many grams, they're wanting me to solve for grams. Okay, so I know I'm ending here, grams, but I always need to figure out of who, grams of who in this chemical reaction. Grams of silver chloride. Well, where's silver chloride? There he is. So I always like to map out what it is I'm solving for and write it underneath that substance in the chemical reaction, because all stoichiometry needs this mole ratio step so I can more easily visualize and remember what coefficient I need to grab when I get to that mole ratio step. Okay, so that was where I'm going to. Now I'm going to be looking for my given, which is the numbers that they start me off in the problem. You're like, what is going on? There's two numbers here. Well, you can't start with a molarity. Okay, you can either start with a grams or a liters. I actually use, as we mentioned before, molarity is going to be probably a conversion factor to help me. So if I have a choice of starting off with mass in grams or volume in liters or milliliters, this is my starting or my given information, that 50.0 milliliters, okay? I'm gonna underline this entire thing. 0.45 molar is important. That is the concentration of that silver nitrate solution. I will probably, in fact, I will use that as a conversion factor to convert from that volume to the moles as my first step. Okay, so underneath my silver nitrate, just like I did with my unknown, I'm gonna find my given, there he is, and I'm gonna write the given information that I have underneath him. That will let me know where I'm starting from. So they gave me 50.0 milliliters. I also like to, at this time, circle the number that I will be pulling down for the mole ratio when I jump over that dotted line. Stop talking about silver nitrate to start talking about silver chloride. Okay, so here we go. We're ready to go. We're super excited. Or maybe we're not only slightly excited, but I'm super excited. Okay, so my given is what's going to go up here first. This is where I'm starting. But if you're noticing, I've got to make that a liters representation, right? So to convert from milliliters to liters, I just have to rock the decimal place back 3 times that way. So this in liters is going to be 0.0500, and this is liters. I did not give myself enough space. AgNO3, okay? You're like, great, now what do I do? They've given me the molarity for a reason. This molarity can state for me, I'm making a stretch putting this way up here in the notes. This states that there is 0.450 moles in every 1 liter of silver nitrate. I'm going to use that down here. The way I'm going to orient that depends on my ability to cancel off units on top and on bottom. I have liters here. I need liters down here. So the way that I'm going to write my molarity for this silver nitrate, still my given substance, so I'm still going to be using green for this entire conversion factor, is I'm going to have the 1 liter part on the bottom and then the moles part on the top, which we said was 0.450 moles of silver nitrate. So all I've done here, you guys, is I've used molarity. So this is molarity. That's what I've done here. Molarity. Oh my gosh, thank you, molarity, for being so helpful. That then has gotten me, oh good, we've made it to moles. Remember, all stoichiometry is just a race to get to your given moles, because then we know my next step is applying that mole ratio, where I get to switch my colors, stop talking about my silver nitrate and start talking about my silver chloride. Okay, so for the mole ratio, y'all, we circled the numbers we get to use in the mole ratio. That was a 2. This states that for every 2 moles of silver nitrate, I have 2 moles of silver chloride. And if you want, this is our first example that we've done together, we can maybe circle those numbers so that way you know where you've gotten that information from our balanced chemical reaction. And I oriented that way so I could cancel out moles of silver nitrate on top and on bottom, okay? So this step gets me to moles of silver chloride, but I'm not done. I'm like, I've even forgot where I'm going. Well, you've not forgotten because you've taken the time to write where you're going to. I want to take it to grams. We've done moles to grams for like months now at this point. I just get to use the molar mass, which states that for every 1 mole of silver chloride, I have a certain number of grams of silver chloride. You're like, how am I supposed to know the certain number of grams of silver chloride? Well, I get to find silver on my periodic table, and I get to find chlorine on my periodic table. I have 1 of each of those, so I get to add that decimal number together, and that will give me the mass of 1 mole of silver chloride. So I have 107.87 for that 1 silver that I have, plus, and then my chlorine is 35.45. So 35.45, which means my molar mass of silver chloride is 143.32. So I get to write that in, 143.32. orienting that molar mass this way so that I can cancel off moles of silver chloride on top and on bottom. So this last half we've been doing for a long time. The only thing new I've added in here is I now get to use molarity as a conversion factor, just like I have the ability to use a molar mass as a conversion factor. Okay, so if I type this into my calculator, I will hopefully get the answer to how many grams of silver chloride will precipitate out from this reaction equation, right? So I have 0.05 times 0.45 times 2 times 143.32 equals, and then I divide by anything that's of importance on the bottom. Everything else is a 1 except for this 2, so I'm going to say divided by 2. Okay, so that is, what is even that number stand for? You've not forgotten because there's something you have not crossed off. That is the units of your answer. Okay, so sig figs of it all, it looks like that's got 3 sig figs. This number has 1, 2, 3 sig figs. Yes, that trailing 0 is important because there's a decimal in the number. No leading zeros are never important regardless of the decimal and where it is in proximity to that. So my answer has to be 3 sig figs, right? So my answer is going to be, and I think I'm going to still use my red because this is my ending substance and I like to keep it the good theme, 3.22, and the units are grams, and of silver chloride. Yes. Okay. So that was our first little stoichiometry problem. I first had to write the balanced chemical equation. Then I identified what they're asking me to solve for, write that information underneath the reaction equation of the substance that I'm trying to get to, then identify what the given information it is. If they've given me a volume, hold on to the molarity because we'll be using that as a conversion factor. So converting from my given to my ending. Once again, the only step where you see the switching colors is my mole ratio step, which is why those numbers from the balanced chemical equation are super important to me. Okay, we only have one more practice problem to do because once we start kind of expanding our ability to do stoichiometry with kind of just new things, it starts to become a little bit, I guess easier, honestly, because we have that understanding of that skill already built in. So our last problem that we're going to do, our second and our last, says how many milliliters of y'all, there's no chemical reaction. I cannot do nothing until I get that chemical reaction. What is going on here? So it says I'm taking barium nitrate is going to react completely with aluminum sulfate. So barium nitrate is going to react completely with aluminum sulfate. So those are my 2 reactants. It looks like a compound between barium and nitrate, ionic compound, another compound between aluminum sulfate, another ionic compound, you guys. Okay, double replacement reaction coming our way. Barium nitrate. Barium's got a +2 charge, right? Nitrate, the polyatomic ion, has a -1 charge. So my formula for my first reactant, barium 2 nitrate, is BaNO3 2. Yes? Cool. Because I need 2 nitrates, each with a -1 charge, to neutralize or cancel off that 1 barium with a +2 charge. Okay, next reactant we said was aluminum sulfate. Aluminum has a +3 charge. Sulfate polyatomic ion, who is SO4, has a -2 charge. So this one's going to be a little bit more interesting. That means as a result of the crisscross, those 3's and 2's swapping places to represent the subscripts of the opposite ion, I would have Al2, SO4, 3. Amazing. So double replacement reaction, which means these guys are going to swap partners, get rid of any subscripts onto each one of those ions. We're going to start a fresh crisscross from scratch between the 2 ions according to their charges, which means barium cation is going to pair up with the sulfate anion. Luckily, barium has a +2, sulfate has a -2, so that means it's going to be a 1-to-1 ratio of those ions. So my formula is BaSO4. I'm going to keep the parentheses around that sulfate because balancing will be easier with that being done. And then my second compound is going to be between the nitrate and the aluminum. Write the positive aluminum cation first and the nitrate anion second. Do not bring those subscripts over. The formula for aluminum nitrate needs to be according to what their charges is from scratch. So nitrate has a -1 and aluminum has a +3. So the 3's and the 1's swap places. So my formula for aluminum nitrate is AlNO3. Okay, balancing, we know we need to balance this going at the end. Well, it looks like, what do we got going on here? I have 2 aluminums over here, and I only have 1 over here. So how about we start off by putting a 2 in front of aluminum nitrate on the product side. Then I got now 2 times 3 nitrates over here to get 2 times 3, that's 6. So how can I get 6 nitrates over here? What times 2 can I multiply that nitrate by? 3. So that gives me 6 nitrates. That also changes my bariums to be 3 now. Well, how about I put a 3 here in front of barium sulfate? You're like, this is getting squirrely. It's fine, because look, now I have 3 sulfates to match the 3 over here. We are finally balanced. That was a fun one. Okay, so now we're ready to read the problem. How many milliliters? How many milliliters? How many milliliters? How many milliliters? Milliliters is where I'm ending up. Milliliters of who? Oh my gosh, that's just the concentration of the barium nitrate that I'm going to be finding the milliliters for. So underneath the barium nitrate, here he is. I get to write question mark ml. And if you want to even kind of specify that we will technically solve for the milliliters after we get to the liters, because that is where my molarity will take me, which is where I'm eventually have to use that 0.3 molar. I'm like, oh my gosh, I said too many things at once. I'm sorry. But here is the number that we'll be using for our mole ratio step when we get to our ending substance. Now, what did they give me? What did they give me? What did they give me? Oh, they gave me 100 milliliters of, 0.5 molar aluminum sulfate. Once again, those molarities are just for conversion factors. They're not going to be my given or my unknown. Okay, so aluminum sulfate, oh, there he is. So I'm going to be starting with that 100 milliliters of aluminum sulfate. So I'm going from liters of a solution up through moles, down to the liters of solution, using each one of these guys' respective molarities oriented in a way that will allow me to convert in the direction that I need to. So we are ready to go. So I'm going to set up my train tracks for converting, and I'm going to put my given information. You know, this is going to actually be super long because look at these chemical formulas. I'm sorry. Okay, but I'm going to maybe give myself more space than I typically do. So my starting is milliliters. Oh, I've got to make sure I represent that in liters. So 100 milliliters is technically 0.100 liters. And this is of who? I'm going to have to write real small. Al2SO4 3. Yes? Going from liters to moles, I'm using the molarity. The molarity of aluminum sulfate we said was a 0.5 molar solution. That means there are 0.5 moles in every 1 liter. Well, the 1 liter part needs to go on the bottom because I want to be able to cancel things off on top and on bottom. So 0.50 moles per 1 liter. That is what that expands into with that split unit. Once again, on top and on bottom, oh, not silver, Al2SO4 3, and this is Al2SO4 3. Once again, whenever I'm using molarity as a conversion factor, it better be all the same color, the same stuff, right? That was all for aluminum sulfate. So now I can cancel off liters of aluminum sulfate on top and on bottom. I've made it to my given moles. Whew, made it to given moles, made it to given moles. It is mole ratio time. I almost forgot to circle my coefficient for my given aluminum sulfate, right? It is a 1-to-3 ratio between those two things. That 1 needs to go down here and the 3 on top because I want to cancel out the moles of aluminum sulfate on top and on bottom from the previous step. Okay, so I have 1 mole of Al2SO4 3. For every 3 moles of BaNO3 2. Okay, so once again, these numbers that I'm getting from my mole ratio step where I start splitting my colors, stop talking about aluminum sulfate and start talking about barium nitrate, I'm getting those from the balanced chemical reaction. So that cancels out. I've made it to moles. And my final guy, my barium nitrate, but I'm not asking you to solve for moles of barium and nitrate. I'm asking you to solve for the volume. Okay, that means I need to convert moles to volume somehow. That's using my molarity. My molarium equates how many moles you have in a certain volume in liters of solution. Well, the molarity for barium nitrate is, oh, here it is, 0.3 molars. That means that there is 0.3 moles in every 1 liter of solution. Well, I need the mole part on bottom this time, which means I need the 0.30 moles per every 1 liters. Okay, so that is me taking this and saying that is 0.3 moles in every 1 liter. I'm just going to orient it in a way that makes sense for my ability to cancel things off. And this is all red, which means this is all still talking about barium nitrate. Yes, so all I did was to make sure that boom, boom. Okay, so now I gotta just calculate, and that is not a big deal. We can do the hard things. We can do the calculations. So I have 0.1 times 0.5 times 3 equals, and then the only thing on the bottom I have to divide that by is the 0.3. So divided by 0.3. Okay, I get 0.5, yes? So we have 0.5, 0.5, and this is a liters representation. If you'll remember, my answer wouldn't actually technically tell me how many milliliters that is, right? To turn that into milliliters, I just move the decimal 1, 2, 3 places that way. So that is 0, wait, what am I doing? Move it 3 places that way. That's 500 milliliters. But here's the ding-dang tricky thing about this, you guys. Sig figs of it all. Okay, I've got lots of numbers in this problem. This molarity has 2 sig figs. The leading 0 is never significant. That ending 0 is because of the decimal in the number. So 2 sig figs, that has 3 sig figs. This has 2 sig figs. So my limiting is that I need my answer to be 2 sig figs. That means I want this 5, and that means I want that 0, but not that last 0. There's no way for me to, like, if I put a decimal at the end of this, all of those zeros are significant. So for this sneaky answer, I actually have to write it in scientific notation saying, and I should have been using my red. I would write this as 5.0 times 10 to the, where the decimal technically is in this number of 500 is 2 places away. So 2, and the units are liters. I have no room to write my of what, but it is barium nitrate, you guys, okay? So yes. Oh, this is milliliters. Sorry, that was the point. Milliliters, yes? So that was some good Stoic here. And this one was a great problem because it had us using molarity twice for both of the solutions involved in this problem, right? So here was 1 molarity for my aluminum sulfate, that 5 molar solution, which I was able to express as 0.5 moles in every 1 liter. And here was my molarity for the barium nitrate solution, which is why I was able to express a 0.3 molar solution as 0.3 moles in every 1 liter. So I've got molarity actually working hard here. I can use molarity to help me solve stoichiometry problems so I can figure out how many mass amounts or volume amounts of some of these substances involved in chemical reactions in aqueous solutions.